All right, assuming Apple's time server is correct, it's 3 o'clock. Welcome, everyone. I'm Rick Fienberg, AAS Press Officer, and I'm very happy to see so many people here for the fifth and final press conference at this 232nd meeting of the American Astronomical Society, live in Denver, Colorado. Helping me today, monitoring our webcast, is my AAS Media Fellow, Carrie Hensley, in the back corner. We do have a webcast audience. If you have a cell phone or a pager or any other kind of beeping device, please make sure it's on silent. We have 3 press releases going out this afternoon. So if you're on the AAS press list, check your inbox and you'll see press releases. The videos of the previous webcasts have already been posted online. So if you go to the online press kit for the meeting, you'll find the videos from both of yesterday's briefing and from this morning's briefing. This afternoon's video should be online by the end of the day. And once more, I apologize that we weren't able to successfully record Monday's briefing. So if this is your first AAS press conference, let me just give you a quick rundown of how we do it. I'll introduce the topic and all of our speakers at once at the beginning. And then after I've turned it over to the first speaker, each speaker will then follow in succession, and we'll hold questions and answers for the end. That way we won't accidentally cut off anybody. So today's topic is the Milky Way and active galactic nuclei, or AGN, or the bright active centers of galaxies. So we're going to start with a presentation from Bill Reach of SOFIA and the university's Space Research Association on shocked molecular gas and the origin of cosmic rays. Then we're going to look at the galaxy as a whole with Ekta Patel from University of Arizona on estimating the mass of the Milky Way using satellite galaxies. And then we're going to zoom into the hearts of galaxies. We're going to hear from Randy Campbell from the Keck Observatory and Ciurlo from the University of California at Los Angeles on more mystery objects having been detected near the Milky Way's supermassive black hole. And finally, Scott Barrows from the University of Colorado in Boulder will talk about discovering galaxy mergers using offset quasars. And he was given a nice teaser or introduction at the plenary by Julie Comerford earlier today, the lunchtime plenary. So I think we're all eager to see what he's got to say. So with that, I will turn it over to Bill Reach, and we'll get underway. You should be good. You can see your slides there or here.
Okay, good. Thank you. All right, so I'm going to tell you about a project that involves cosmic rays and their origin in molecular shocks. And this is a story of 2 different fields of astrophysics. One is on study of cosmic rays, and the other is on studies of supernova remnants. And these are 2 fields that have been separate, but are gradually coming together like a couple that's known each other for a long time. They always knew they needed each other. But they're finally realizing just how much. So cosmic rays were discovered some time ago. There's a nice presentation earlier in this conference about it. And they have a lot of energy density. They're very important energetically in the galaxy. They have as much energy as all starlight added together. And there are notable things about cosmic rays. The reason we don't think about them too much is because they pass through things almost unimpeded. They have a weak interaction with matter. So they can penetrate. That makes, well, you can just forget about them if they just go through everything. But they do deposit some energy, and they can go places where starlight can't. Okay, and the new development, so this is just quick, okay. The new development that's making this field approach the one that I've been working on, which is on supernova remnants, is that cosmic rays and their high-energy gamma rays are being localized to smaller and smaller areas. So here's an image from the NASA Fermi Observatory, where they found in this 5-degree area, there's one main source in the middle of the image, and that is a supernova remnant. The little radio contours are shown as little squiggles in here. So it's obvious that the source of gamma rays, of high-energy gamma rays in this area, is that supernova remnant. And that's a paper from 2010, so that's not so new. Newer is that the very high-energy particles, so TeV, very high energy particles, TeV particles, can now be localized. And then these results are from the Veritas experiment. I'm not part of this experiment, so this is the other field coming towards mine. And what you see in the two images is a supernova remnant in the color here. That's one of my favorite supernova remnants that I've been working on for some time. Excuse me. And then on top of it are contours of the gamma rays. And what's new is that now the TeV component has been localized, and now not just to a source, but seeing details within it. And so in this image of the supernova remnant here, this is the infrared image, you can see that, yes, the contours are associated, and you can see that they're associated with the blue part and not the red part. And over here is an X-ray image. You would think that TeV, very high energy photons, would be related to X-rays, but they're not. The origin of cosmic rays is not the same as the origin of X-rays. Okay, that's the TeV side. Now, what we're trying to do with studies of supernova remnants in molecular gas is trying to learn what are the properties of the individual shock fronts, and we'll get better and better, and the TeV will get better and better. Okay, so shocks into dense gas from supernova explosions happen often because massive stars live and die close to the same place. They have short lifetimes. Okay. I'm going to skip some of that. So here's a picture of that, a cartoon of that. If you have a molecular cloud, well, here's actual data, a molecular cloud in this gray image, that's a molecular cloud. And then here's a supernova remnant that's right on the edge of it. And then we found places in it where there are active molecular shock fronts. And here's another, is a different supernova remnant, but zooming in detail, we can start to resolve individual shock fronts, and that's what's shown in here. And this is a comparison now of a molecular hydrogen image from a ground-based telescope from the Palomar Observatory with the radio synchrotron emission, showing this we thought was an early evidence for the origin of cosmic rays in these molecular shocks. But now this is at the few arc-second scale, so TeV is not, the high-energy part of the field hasn't approached that yet. Now, in terms of the new thing that we're working on is trying to measure the velocities. So that's one thing we can do with the molecular spectroscopy is we can measure velocities. Here's from the NASA SWAS satellite, old mission, I guess, showing a spectra of many molecules, and the x-axis is velocity, and the point is that when the emission is spread out over many velocities, we can tell about the nature of the shock. But that was a coarse experiment with low angular resolution. And what we're doing now is we're going to use SOFIA, which is airborne observatory, and we're going to try and measure the velocity of the molecular shocks. Okay, so this is that same supernova remnant, and on the right are the actual spectra that we got. It just shows where we looked. We looked in the blue place, which was by design. And then here's an example of another of the spectra. And then here I just wanted to show, because I just learned yesterday, and the presenter of this particular data is here in the room, but I just saw it at a talk here at this meeting. The Ryder-Hubble spectra, also showing shocks into dense gas, and then our SOFIA spectra are on your right-hand side. And what we see, so what you can see is the yellow lines are atmospheric lines, and the white line in the bottom is our data. You can see that they're at different velocities. So we are seeing some of the shock clumps are molecular and accelerated, and that's what we were looking for. This is the initial part of our experiment. We intend to get data on several more supernova remnants and different locations to complement it in the future. Here's the conclusion summary, which you guys can read. The TeV field is going to improve with the advent of the CTA, the Cherenkov Telescope A, whatever A is, in 2022, the CTA. And then on our side, we'll continue to do a spectroscopy of individual shock fronts better and better to measure their velocities. There's my name, there's our press officer, who you can contact for all kinds of other information. That's it.
Okay. Hi, everyone. My name is Ekta Patel, and I'm currently a graduate student at the University of Arizona. Today, I will be telling you about a paper I led that was recently published in the Astrophysical Journal with my collaborators that I've listed. And this work focuses on estimating the mass of our own Milky Way galaxy with a new method that is well suited to utilize the rich data sets that are currently available to us. So first, I wanted to briefly start with an overview of how we think galaxies grow and form and evolve over time. The foundation of this model is dark matter, and in particular, a commonly accepted view is a flavor of dark matter that we called cold dark matter. We believe that this dark matter exists in this filamentary structure that spans the entire universe, as I've shown in the image on the right. This is an image from the Illustris simulation, which is a cosmological simulation, meaning that its aim is to reproduce a large volume of the universe from just after the Big Bang to today, rather than looking at maybe one galaxy in very close detail. These filaments draw the normal or visible matter along with them, so at the intersections of this filamentary structure, gas and dust collapse to form stars, and eventually galaxies grow there. In this model, we think that small structures form first, so this is called a bottom-up structure. And so the small galaxies are forming first, and then they're emerging and forming more massive galaxies. In the process of that, some of the small galaxies become attracted to more massive ones, and they become what we refer to as satellite galaxies. So in this first example, I'm showing an image of a galaxy cluster. Galaxy clusters contain anywhere between 100 to over 1,000 galaxies, and these galaxy clusters form at the densest intersections of this filamentary structure. If we move to slightly smaller scales, we find galaxy groups, like our very own local group. So the local group is home to our Milky Way galaxy and its satellite population, as well as our neighboring galaxy, Andromeda, and its satellite population. So why is a precise Milky Way mass estimate necessary? Many astronomers have published values for the mass of the Milky Way in the past, over the last few decades, and those values in the literature range from about 700 billion to 2 trillion solar masses. So this is quite a wide range, and with this method that I'm presenting to you here today, the hope is that as we get larger and larger data sets, that we can narrow this mass range for the Milky Way. Secondly, understanding a precise Milky Way mass estimate is very useful for galaxy physics. So in general, host galaxy mass controls the number of satellite galaxies you would expect to find around any given galaxy. Host galaxy mass also influences the internal and orbital properties of satellite galaxies. So by internal, I'm referring to things like how dense a satellite galaxy is, how massive it is, how bright it is. And in terms of orbital properties, I'm referring to things like how long does it take for a satellite galaxy to complete one passage around its host. So typically, that's a timescale that is of order a few billion years. But depending on the host galaxy mass, that could go either up or down. And finally, host galaxy mass is very closely related to the mass budget of galaxies. So we think in this cold dark matter theory that about 15% of the mass in a galaxy is in this normal matter where we can actually observe. And the remainder, the remaining 85% of it, is in this dark matter that we can't actually see with our own eyes or even with the best telescopes in the world. So to date, we know of about 50 satellite galaxies that are orbiting around our own Milky Way, some of which I've shown in this image. But simulations predict that there could be 100 or even 200 satellite galaxies of our own Milky Way. So right now, our picture is not quite complete. The motion of these satellite galaxies relative to the Milky Way can be measured using telescopes like the Hubble Space Telescope. So in this movie on the left, I'm showing you the predicted past orbital histories over the last 2 billion years for 11 of the satellite galaxies of the Milky Way. So these 11 are what we refer to as the classical satellite galaxies. They're the most massive and brightest satellites of the Milky Way, and they were also discovered first. You'll notice that the shapes of these orbits are not all identical, and that's helpful to trace the dark matter halo of our Milky Way galaxy. So in our method, we focused on 3 properties that are the distance, the 3D velocity, and the angular momentum of satellite galaxies. So the position and velocity of a satellite will change in time. So I'm showing just a movie here on the right, which is a planet orbiting a star, but this situation is very analogous for a satellite galaxy orbiting around its host, where at the closest point, the satellite will be moving the fastest, and at its farthest point, the satellite will be moving the slowest. So position and velocity are constantly changing as the satellite completes an orbit around its host. On the other hand, we have orbital angular momentum, which is the product of distance and velocity. And this quantity is actually conserved in time as there's a trade-off between position and velocity. So you can think of this if you're thinking about a figure skater who's spinning, whose arms are out, and they'll be spinning slower, and as they move their arms in and decrease the distance between their arms and the rest of their body, their spin will increase. However, throughout that whole process, the skater's angular momentum is conserved over time, and so that's a similar process that's happening with satellite galaxies. So that leads to our first result, which is that angular momentum is the most reliable satellite property for estimating host mass, because it's independent of where a satellite galaxy actually is in its orbit around its host galaxy. So in our method, we compare the measured properties of many satellite galaxies to those of simulated satellite galaxies. So we start with the observed satellites and their properties. So this is an image from Gaia that came out just about a month and a half ago. And then we have a set of satellite galaxy analogs that are chosen from a simulation. In our method, we use the Illustris simulation, which I showed on one of my first slides. And with these two sets of data, we ask, in a statistical sense, how common are these two sets of data, or how similar are they? And when we repeat that process around 20,000 times, we can then form a mass estimate. So for our galaxy, using 9 of its satellite galaxies and the properties I described, simultaneously, we find a Milky Way mass of about 0.96 trillion solar masses. So it's kind of in the middle of the mass range I quoted earlier. I'll emphasize the simultaneously part here because many previous methods have used the properties of just maybe 1 or 2 satellite galaxies. So here we're trying to push the limits of that and really trying to increase as much data as we can. And that will be applicable for more than just the 9 satellites we've used in this method here. The second result is also that this method implies that the Andromeda Galaxy is more massive than our Milky Way by about 30%. So in summary, we've developed a new technique to estimate the mass of the Milky Way that uses the properties of multiple satellite galaxies simultaneously. Our mass estimate is unbiased by satellites that might be in a specific place in their orbit around their host galaxy. Our value for the Milky Way's mass is about 0.96 trillion solar masses. And then most importantly, this method is perfectly suited to take advantage of the current rapid growth in both observational data sets and numerical capabilities. So as we have telescopes like the LSST coming online in the 2020s and Gaia, the ongoing space mission, these data sets are continuing to grow and have grown even since I published this paper a few months ago. And so we're really looking forward to the next generation of simulations and observational data sets that we have. Thank you.
Thank you all for coming today. My name is Randy Campbell. I'm with the Keck Observatory, and thank you, Rick, for including us in this session. we're going to share with you some new results that we came up with, and reanalyzing some data that we have over the last 12 years near the innermost regions of the Milky Way galactic center. My colleagues are listed here, and also I want to point out that we're going to tag team this presentation, and Anna will be giving the second part of the presentation. So to start off with, the center of our galaxy, of course, is very well studied, especially at high angular resolution over the last 12 years at several observatories, and in particular Keck, where I work. The two instruments we use the most are NERC-2 and OSIRIS, and we've determined that, over these studies, several interesting scientific results. Of course, there's a supermassive black hole at the center of the Milky Way. Everybody knows that. But also there's a lot of interesting other results from this. Let's see here. Is that animation going to play? Oh, it is playing. Okay. It's not playing on mine. Okay. Yeah. Okay. So there's a cluster of young stars near this black hole, and it's a mystery on how these young stars could have gotten there. It's unlikely they could have formed there, so that's a mystery. Also, this year we're doing a campaign on the star SO2, which is doing its closest approach to the black hole and is a nice test of general relativity. But that's not what this press release is about. We're reanalyzing some some OSIRIS data. We originally intended to look at some of the gas dynamics in this very inner region, and we had some kind of surprising results. But using the OSIRIS data over the last 12 years, OSIRIS is an integral field spectrometer, which gives you imaging and spectroscopy all in one data cube. So it's a very powerful tool. And we are reanalyzing those data to look at the gas near this innermost region of the black hole. We created a tool to help us with that. Since the OSIRIS data cube is three-dimensional, we're analyzing these data in 3D. And if you can take a cube and turn it into a volume rendering, and it reveals features that might otherwise be hidden in either the imaging or just the spectra. And so this tool has allowed us to identify some new interesting features that fit into what we think are the G object class. And I'm pointing out 3 of the ones that we're now studying in more detail, G3, 4, and 5, named since they have similar properties to the other objects known as G1 and G2. Those properties are that they have hydrogen emission, as shown here in this spectrum. They're very red, and they don't have a stellar continuum. They're not detected in shorter wavelengths. They're only detected either in this hydrogen emission or in the thermal infrared. They're compact sources, and they have high proper motion and orbits that bring them close to the supermassive black hole. Those motions are shown in this next graphic, where if I cut out just the blue shifted part of the spectrum and show it down on the lower left and play an animation over the last 12 years, you can see the motion of G3 and G4 as they progress through the 12 years. G4 is moving to the west and G3 moving up to the northeast. Similarly, if I cut out the red portion of the spectrum and animate that, I can see the G5 proper motion as it's looks like it's headed right for the black hole. Is that animating? Okay, there we go. So that's showing the proper motion feature of the G objects. We also have NERC2 thermal imaging, where they're also detected at L band. This image is a combination of 2 wavelengths, K and L. The K is depicted as blue and L red, so the very red objects are jumping out. And for comparison, you can see also the G1 and G2. Actually, the arrows are a little bit off center there, but so they fit all of the characteristics of the G objects, G1 and G2, and therefore we've labeled them. G5 in this picture is perhaps source confused. One of the things that's unique about our study compared to the other G object studies is that we've used the bracket gamma feature to pick them out in the 3 dimensions. And so G5 would have been missed in this, and so the 3-dimensional analysis is one of the strengths in this new study. And at this point, I'm going to turn it over to Anna.
Thanks, Randy. Hi, everyone. So I'm going to start over from here. So thanks to this very nice data set, we could disentangle and study closely G3, 4, and 5. So what I'm going to show you here is actually the motion of these objects over the years. So in this plot, you have the motion of stars in red. For example, we have SO2, the star that just went through closest approach a few weeks ago. You have in blue the already known and studied G1 and G2 object, and in green G3, 4, and 5, our new objects. So in this graph, we are showing you data that we have with OSIRIS starting in 2006 with the green points and going all the way to 2017 with the yellow points. The arrows are showing you the motion of the object, and the solid line for the green points is showing you the model. Because since we have information about their position and their velocity thanks to OSIRIS dataset, we can now start to model their motion around supermassive black hole, which means that we are starting to have information about their orbits. So as you can see, just looking at the arrows for the green points, G3 and 5 are going toward the black hole while G4 is moving away. And since we studied the orbits, we know something more about their movement. We know, for example, that G3 probably has a period of around 200 years and is moving on an orbit that is very close to being circular. On the other hand, G5 is moving on a very eccentric orbit, so it means that it's very elliptical, and we think that the closest approach, the closest encounter between just this object and the supermassive black hole Sagittarius A star that is shown by the cross in the plot is going to happen in 15 to 30 years, maybe more. On the other hand, G4 is moving away from the black hole, so maybe already passed through its closest approach to the black hole and could maybe come back in a few hundred years. The problem with G4 is that the model is not very well constrained. You can tell because the solid line doesn't go through G4 points as well as it does for G3 and 5. So maybe this is actually not in orbital motion around supermassive black hole. This is preliminary result, I have to point out, with analysis is still ongoing, and so we will have to make these measurements more precise as we add more observation and we go deeper in the analysis of the orbits. But we can start already asking ourselves the most interesting question, that is, what are these objects? So we believe that G objects can be described as stellar, massive objects surrounded by a thick layer of dust and gas. So basically, it's a star that has been puffed up. So the question is, what happened to the star that make it so big? So this is still debated, and there are many hypotheses that have been advanced on the explanation to this phenomenon, but our preferred explanation is that these are the produce of binary mergers. So binary mergers have been described in a variety of literature, but here we're going to reference Stefan et al. 2016 that described the binary mergers mechanism in the context of the presence of a supermassive black hole, as is the case for the galactic center. So on the right, you have a picture showing you how this mechanism roughly works. So you have two stars orbiting around each other and together orbiting around supermassive black hole. What happens is that the presence of the supermassive black hole perturbs the orbits of these stars that becomes more and more elliptical until the stars can actually touch, they kiss each other, and they merge. So when this couple is melted forever, no divorce here, we can actually produce a star that is more massive. And we like this hypothesis and this explanation very much because basically with this mechanism, you produce a star that is more massive than the two stars you started with, and also that look young because they've just been formed. And we know that at the galactic center we have a lot of stars that are young, massive, and very bright. These are the S stars, of which the origin we are still debating about, because in the extreme region of the supermassive black hole you should not have star formation. But it turns out this G object could actually one day, when all the gas and dust goes away, turns out to be bright young stars that actually are the S stars. So in this picture, G object would be like an intermediate step between the binary merger and then having the S stars. So that still needs to be proved, but it's a very fascinating idea, and we think it's very likely, actually. So just to summarize, thanks to 12 years of data taken at Keck with spectrum imaging data and this very nice three-dimensional visualizing tool, we were able to disentangle and very closely follow new bright G objects, and this is still preliminary. We're going to go farther with that, but this helps us interrogate ourselves on their origin and the future of these objects. Like, we believe they are actually the result of binary emergence, and we think they might turn out to be the progenitors of S stars. So we need to gather more data, we need to look for other of these objects, but what's interesting is that, so it's not surprising to have G object at the galactic center if there are binary mergers, because we know there are a lot of binaries, and we know the black hole actually enhances binary mergers. So we need still to go on, but maybe this will help us understand and solve the mystery of G objects, and maybe meanwhile also solve the mystery of F stars. This is just to show you how rich this data set is and also how rich this region is. Because the galactic center is not only the closest supermassive black hole to us, but it's so dense that every single small process going on is going to tell you a lot about this mysterious, but for that still very fascinating environment. And so that's all for now. Thank you very much.
just going to full screen here. Okay, oh, that did not work. Okay, all right, thanks. And thanks for being here. Okay, so I apologize for my voice a little bit. I'm recovering from a cold, actually, so I'll do my best to be audible. I'll be talking about discovering galaxy mergers using offset quasars. And this is work that I've done with my co-authors listed at the bottom of this slide. So before I begin, I guess I want to set the context for the relevance of this by saying that galaxy mergers are observed to be fairly common in the universe. And what's shown on this slide is a merger between two similar-sized galaxies that is similar to what we predict the merger between our own Milky Way galaxy and the Andromeda galaxy is going to be like. And when that happens, one thing that may happen is the force of this merger is going to drive a lot of gas and dust down to the centers of these galaxies where the massive black holes reside, potentially powering quasars there. And this could happen in one or both of the galaxies. And so this has long been predicted theoretically to be a spectacular event. So this is one recent simulation showing the evolution of the numerical evolution of mergers in these 4 panels here. And then on the very bottom, it shows the evolution of the brightness of the quasars in the galaxy. And one thing that we notice is that the brightness tends to peak at the very latest stages of those mergers when the black holes are really close together. And this is the most interesting regime that we want to investigate observationally. But unfortunately, it's really difficult to find these types of mergers, especially when you can't resolve the individual galaxies themselves. So one of the questions that we've been asking ourselves is, so what's a good way to find these things, right? How can we find them and observationally test these predictions? So we've been doing that using what we're calling offset quasars here. So it goes something like this. Find a galaxy from your favorite optical survey. So in this case, the Sloan Digital Sky Survey. And these are the images in the left panels of each figure. Okay, and then cross-match with the Chandra X-ray Observatory. And we do this because quasars are distinctly bright in X-rays. Okay, and so those are the grayish purple pixels shown in the right panels of each figure. And if you can't see them too well, they're sort of highlighted by the cyan ellipses as well. And those are overlaid on the optical contours of the galaxy. And then what we do is look for cases where the quasars actually spatially offset from the center of the galaxy, the optical galaxy, that is. So it's important to keep in mind here that we traditionally expect quasars to be in the centers of galaxies. So if you see one that's not there, that's implying that a merger has taken place. So what we really want to do at this point is understand just what it is about a galaxy merger that switches on a quasar. Okay, so these are the offset quasars here. What we want to do is understand what it is about a galaxy merger that switches on these quasars. And so to do that, we've had to go to HST imaging, the Hubble Space Telescope, to get higher resolution. And so we've done that for a subset of our sample, and I'm going to show a couple of examples that illustrate broadly the results that we've been finding. So these are the images from the Sloan Digital Sky Survey. If you can see them, the dashed cyan ellipses represent the locations of the quasars. Note that one actually has 2 quasars in it. And so this is the Hubble Space Telescope imaging here. And so in both cases, they reveal signs of galaxy mergers, but interestingly, 2 very different types of galaxy merger. So on the left-hand side, the 2 galaxies are of roughly similar mass. And on the right-hand side, the 2 galaxies are actually of very different mass. The larger one is dominating the field of view, and then the smaller one is kind of down and to the right there. Okay, and just for reference, these are the locations of the quasars within these HST images here. So what are we learning from this new data? Why is it important? Well, one thing that it allows us to do is to go about selecting galaxy mergers with very small separations. Okay, so these are on the order of a few thousand light years or so in separation. It's much smaller than the scale of a galaxy. And this is when the quasar activity is most extreme. Okay, at least that's what's predicted theoretically, and that's what we find. Okay. Also, it allows us to go about determining the number of quasars and their location within the merger. Okay, so to actually study where they are when they're turned on. And then finally, it allows us to find mergers where one galaxy is much smaller than the other. So that image there on the right is an example of that. Okay, the ratio is about 50 to 1 actually. So these types of mergers are much more common than mergers of similar sized galaxies, but they're very, very hard to find. They would be missed by most selections of mergers. And one of the really interesting results that we're finding with this data that I want to share is that it seems that mergers that only have one quasar tend to have very unequal masses of galaxies. Their sizes are very unequal. Okay. And this seems to imply that single quasars in the merger-driven scenario are associated with less violent mergers. So my contact information is at the bottom of the slide for more information, and I want to thank you for your time.
All right, thanks very much. Lots of interesting stuff to talk about here. So we're going to start by taking questions from here in the room. I want to remind you to wait for a microphone. Do I have a microphone handler? Ah, great, Gaurav, thank you. So wait for Gaurav to bring you the microphone, and then identify yourself by name and affiliation, and let us know who you want to address your question to. If you're on the webcast, please queue up your questions for Carrie via the text chat. All right, so we'll start here with Jake. Oh, sorry. Gaurav, I was pointing here. I'm sorry, I didn't see you back there, but we'll go to you next. All right. I can't see anybody who's sitting directly under a light.
Hi, Jake Parks, Astronomy Magazine. This question is for Randall and Anna. So basically, I'm wondering if the G stars are forming from these binary stars, where are these binary stars coming from, in the sense that you were talking about how stars don't really form around supermassive black holes. So I guess, where are they coming from in the first place?
Well, what you'd expect in this region is a population of older stars. And in a typical stellar population, there's a high percentage of binaries. And so what people would expect is older stars with a bunch of binaries. But what we see is there's a lack of older stars and this population of young stars that are not easily explained.
Yeah, and you could have formed the old stars somewhere else and have them brought in the center. So it's not a problem to see old stars. It's just puzzling to see young stars.
Okay, so now we'll go to the back, to Kala.
Hello, Kala Perkins from Infinity Education. This is for Scott. So I'm used to the definition of quasars being the very hot cores of young galaxies, very powerful cores of young galaxies. And excuse my ignorance, but so I'm not quite understanding the turning on of quasars in these galaxy mergers and the relationship of my understanding of what quasars were to what you've been sharing with us. Thank you.
Sure. So yes, it would be good to clarify. So by quasar, we mean a supermassive black hole that is eating a lot of material, and some of that energy is eliminated as electromagnetic radiation. And so that's just a quasar is sort of the term we're using for that. But this can happen in any galaxy with a supermassive black hole that's able to get fueled this way.
So you're talking about reigniting dynamics around existing black holes in galaxy mergers as quasars?
Yes, possibly reigniting or igniting for the first time.
Okay, thank you.
Okay. More questions here in the room? Okay, down in front. Nola.
Hi, Nola Red, freelance. My question's for Scott. So in the talk this morning, Julie was saying that like most of the fueling of the AGN comes at the end of the lifetime. Is that? Do you see that also with the quasars you've got here?
By lifetime, do you mean of the merger?
Yeah, the lifetime of the merger.
Sure. Yes. So that is a general result that we're seeing with all of our data.
I have a quick follow-up for also for you, Scott. You showed the pictures of the two very different merger scenarios. One had a single quasar in it, and the other had two. But then you later said that it was the ones with the most unequal masses typically had one quasar in them. So you showed an example of a very massive galaxy absorbing a much smaller galaxy and it had two quasars, but then said that, I think you said that in that scenario, you more often find one quasar. So I was just curious, were you just showing an atypical example, or did I mishear you?
You heard me right. So you're paying attention, and I like that.
It's part of my job.
Yeah. So that was it's sort of an atypical example, so I should clarify. So I was trying to be very careful to say that for galaxies with only one quasar, we almost always see them as having very large mass ratios or unequal sizes. But for galaxies with two quasars, it's not quite as simple. They tend to, they do overall tend to have very more comparable sizes, but we think that other factors are at play too for igniting two quasars other than just the mass ratio.
Okay. All right, we'll come back to Nola.
Sorry, so following up Rick's question, would the two likely sizes, like to have a quasar, would the galaxies have to be more likely similar sizes versus big and a small without a quasar? Does that make sense?
I think so. Are you asking if to have two quasars, do we need two similar sized galaxies?
I mean, yeah, the requirements to have a quasar in the first place would be the similar size, yeah.
I suppose generally yes. Somehow material has to get down to the black hole to fuel it and switch on a quasar. And we, numerically and theoretically, we expect that mergers between galaxies of similar mass are going to be more violent and have forces that are able to sort of drive this inward flow.
Okay, we'll take one down here. Carrie, do we have any queuing up online? Okay, we'll go online next.
Steve Marin, freelance for Bill Reach. If Enrico Fermi was back here today, would he consider this evidence of his mechanism for cosmic ray accelerator, or is it something quite different?
The answer is yes. In fact, I was just rereading his 1949 paper about this, and it was very prescient. What he described is what we now call second-order Fermi acceleration, and what we think is actually happening is what was later called, not by him, but first-order Fermi acceleration. But when he would have loved to see that his general idea that a swept-up magnetic field can form a wall that accelerates particles, that is happening. He might not have predicted the exact environments, but yes, I think it is overall confirmation of the principles he put forth in 1949.
Okay, we're going to go online for a minute, then we'll come back to the room.
All right, this question comes from Camille Carlisle at Sky and Telescope, and this question is for Randy and Anna. Are you able to tell how the orbits of these new objects compare to those of G1, G2, and the S stars? And specifically, are they as eccentric as G1 and G2's orbits, and what are their distances of closest approach to the black hole?
So some of them are as eccentric as G1 and G2, but not all of them. Like G5 is on a very eccentric orbit, very, very eccentric. It looks like G1 orbit, but like G3 is not. It's pretty circular. So these are just preliminary results, but it looks like some of them are more close to G1 and G2 orbits, and some are different. So then the question would be, then are all those of the same origin or not? For now, the hypothesis of yes, but this region is so complicated that we might have different process going on and different things that can perturb one history of one of these objects. And as for the distance of closest approach, we have not computed it yet. It's going to be out soon. We are going to work on a paper on that, and so we are going to be able to release this information soon, but not quite yet. Sorry.
And then related to the S-stars, they are fairly consistent to the S-stars. The orbital periods we're looking at are on the order of 200 to 400 years, and that's not too far out of the distribution of S-stars. Some of the S-stars have very, very shorter orbital periods, but it's not too different.
Okay.
So we have another question for Randy and Anna from Camille Carlisle. Statistically speaking, how many merger products would you expect to find in the galactic center? And how many other dusty red objects do you see in the data?
Okay. You should look at the Stefan et al. Paper, 2016, because that's where they compute the most precise rate of binary that already should have merged. Because then the question is that, of course, you see S-stars and you believe these stars come from the mergers, but also you see merger products. So there must have been two different waves of events. One first star formation events where then star merged and formed the S-stars, and a more recent one that produced the G objects. So when I think we believe that after, we know that should have been a one star formation event like 6 million years ago, I think. Don't sign me on the number exactly, and so this is consistent for the G objects. And we believe that we should see like 10-20% of the binary mergers, so we should see many of the G objects. How many exactly is not clear yet, and we see other objects that are not quite showing the exact same properties as the other G objects, so we have not called them G objects yet. But also, this is a field that is very complicated, so we have to dig in more to look for other of these objects. I'm sure there are others.
Thank you.
All right, we'll come back to the room. So we have one in the back corner, and then, well, hold on. Please wait for the mic and identify yourself. Thanks.
All right, I'm John Middleditch. I have a mechanism for ejecting material out of near supermassive black holes. My eye poster coming up later this afternoon, predicting the next local supernova, uses it, and it references a paper where I go through the math. That's also it's also in my website. It's online. Okay.
All right, so we'll look for that in the eye poster session this afternoon. Okay, we'll come back over here to Jake, and then we'll come back down in the front.
So for Scott, so if we're finding single quasars typically in these unequally sized merging galaxies, I'm wondering is this implying that only one supermassive black hole of the galaxy is getting enough fuel to actually turn into a quasar, or are we assuming that one of the supermassive black holes got kind of ejected from the merger of the galaxy in the first place?
It's the first one.
Hi, my name is Terry Hsu from the College in New Jersey. I think it just cut out. No,
you're there.
My question's for Ekta. Great talk. Your second result was you found the mass of the Milky Way estimated, which is great. But what was the uncertainty of that number? Like, is that likely to change in the future? What is your plan for that?
Yeah, that's a great question. This is why I don't quote my result as the most precise mass estimate yet. So the error is about 300 billion, so about almost 30%. But the benefit is that with this method, so far we're using either 8 or 9 satellite galaxies. With Gaia DR2, Gaia's measured the proper motions of 30 new dwarf galaxies orbiting around the Milky Way. The reason they're not incorporated in the method, and I don't have an updated answer right now, is because the simulations are actually somewhat lagging, and you need both to be able to come up with a new mass estimate. But the hope is as you add more of those satellite galaxies in, that number should go down. So yeah, the error is not fantastic right now, but this is why as we move forward, we're hoping that that's what will happen.
All right, thank you very much.
Okay.
Steve Lawrence, Hofstra University. For Ekta, and I think perhaps you may have just answered my question, but I'm wondering, with the 9 satellites you have, do you have any measure of the shape of the dark matter halo, or even more, any asymmetries or irregularities?
Yeah, that's a great question.
Is it not a triaxial?
Very good question. That's not something we look at in this work. However, the other student that works with my advisor, his name is Nico Garavito Camargo, is working on that exactly. So he's looking at how the fact that the Large Magellanic Cloud has just recently come very close to the Milky Way and made a pericentric passage. He's actually looking at how that changes what we think the dark matter halo shape is of the Milky Way. So my method does not. It's more of a statistical method that looks at just the general properties of a halo and its satellites. But yeah, that's a really good question, and in the future we're hoping to sort of combine the two methods and move forward that way.
You have a question yourself, Gaurav?
Question, yes.
Okay.
It's for Ekta as well. Great talk. Thanks. Following up on Terry's question, how much do the constraints on the mass change when you use, let's say, one dwarf galaxy to 4 to 6 to 9?
Yeah.
Could you talk a little bit about that?
Yeah, sure. So in the paper that came before this one, we did exactly that. So we just used the properties of one satellite to make a mass estimate for both the Milky Way as well as Andromeda. And so the errors, I believe, on that, when we use the properties of the Large Magellanic Cloud, and specifically its orbital angular momentum, the errors are much larger. So I think the error was about 1.7 billion as a upper limit, yeah, and then the lower limit was like 700 billion. So it's much larger with one satellite.
I have a couple of related follow-ups too. Can you, first of all, the masses that you're measuring includes all the baryonic matter inside that radius, basically, as well as the dark matter, right? So it's a total mass, or is it excluding some fraction of either of those?
So we're using, so the illustrious simulation has 2 versions. There's one that is just the dark matter, and then there's one that's the dark matter plus the hydrodynamics. We focus on just the dark matter because when you're looking at these very low mass galaxies, there are some very well-known problems that pop up when you add the baryons in that preferentially destroy some of those low mass galaxies, which would then just bias the method entirely. So we're focusing on the dark matter, but given that dark matter is a large majority of these galaxies, I think it's fair to say that, if you included the baryons, it's all within the error bars of the estimates we're getting. So.
Okay, and then how far out does your ensemble of dwarfs go relative, say, to the size of that we expect the dark matter halo of our galaxy to be, or even how far out relative to where Andromeda is?
Yeah, that's a great question. So in our satellite sample, where the farthest galaxy we're using is Leo 1, which is at 260 kiloparsecs away. So there's some debate about whether Leo 1 is actually bound to the Milky Way or not.
So that's like 3 or 4 times farther than the Magellanic Clouds? Something like that? Okay.
Yep. So it's pretty much, I think, what you would call, close to the end of our galaxy's halo. And then what was the second part of your question?
And relative to the distance to M31. So that sounds like
so M31 is like 800 kiloparsecs away. So that's 4 times farther.
It's a significant fraction, but not like halfway out or anything.
Yeah.
Okay, and then my final question is, have you been in touch with Stephen Colbert?
I have not.
Okay, for those of you who don't know what I'm talking about, this is not the first time that the mass of the Milky Way has been presented in a briefing at the AAS. Steve Marin remembers it all too well. And Stephen Colbert, who then was playing the part of a right-wing bloviator, he was very happy that in that earlier result, the Milky Way came out on top, or as he called it, America's galaxy. But he needs to be informed that, right now it looks not so good for America's galaxy. I don't know whose Galaxy M31 is. Do we have any more online? Good, all right, let's take one of those.
All right, so this question comes from Rick Lovett, freelance, and this is for Randy and Anna. He asks, what is the historical basis of the terminology that you use? Why is it G objects and S stars as opposed to other
letters? Nobody wants to take that.
So for the G objects, I'm not totally sure what's the story, because they have been called like G object, or also a dusty stellar object. So we were wondering about this with Randy actually some weeks ago, and wondering if G was for gas, because the first interpretation is that these are actually only gas clouds, which turn out not to be the case, because G2, for example, survived its closest approach to the black hole and it's not been destroyed by the black hole forces itself, so it must have a very big mass at the center that kept it together. And as for the S stars, do you have a...
I think they just numbered them with an S to
Yeah.
indicate star.
And
now they're called S stars.
Yeah, it might be as simple as that. And so G for gas and S for star. Well, that's very explanatory. But I have to say I'm not totally sure about the real history behind it. So.
Well, I think that suggests to me the answer to my other question, which was for the two of you, which is, what was X7? Is it an X-ray source? It was the brightest thing in your images, but you didn't mention it.
Yeah, that is a good question. X7 has a lot of the same properties as the G sources. It's very red. It's very bright in the bracket gamma hydrogen emission, and it has proper motion. However, it's very well resolved. It's got a very large extent to it relative to the black hole. So one of the characteristics of the G objects is that they're compact stellar objects. And so it was excluded as a G object, but yet it's still very interesting. And I think as we study this further, it may lend some clues as to what the true nature of these G objects are, which is still very, very open question. We right now prefer the binary merger explanation, but there are a lot of other competing hypotheses at this point. So,
just to add a detail, so for X7, we're not that sure that there is actually a stellar object in the middle. So it's still open for X7 whether it's just a gas feature. I know it's a very big feature that we didn't talk about, but this was focused on G object. But we are working on X7 too in collaboration with other people in the group, like the Institute of Astrophysics of Andalusia, and so we're going to hear about it too in a little bit.
Okay.
Yeah, the naming was hard. It's kind of like writing software program. It's hard to name it in the end. So
you could crowdsource it like some of the other teams do now. Anything else online? Do we have any more questions here in the room? Okay, one in the back here.
Hi, Anne-Marie Madigan, not a reporter. This is for Randall and Anna. So you talked about G3, 4, and 5. I'm just wondering, do you have any updates on G2? We haven't heard anything about it post-Pericenter in a while. Any updates on orbital properties or anything like this?
Yeah, we did not, since we started off looking just at the gas at lower radial velocities, G1 and G2 were somewhat excluded from our data set, and we didn't happen to study them as part of this. Now that we've found more of these G objects and the fact that they're turning out to be maybe more common than originally thought, I think we would like to go back and expand. So the radial velocity of G2 and G1 are on the order of 2,000 to 3,000 kilometers per second compared to these, which are just a few hundred kilometers per second. So when we cut the slice out of the data cube to look at the gas, they were actually excluded from this. And they're also not quite as bright as these new objects are really bright, and they just jumped out and said, "Oh, we gotta pay attention to these." So.
Yes, and also so it's harder to see them in bracket gamma. They are not as bright as the sources we presented that so are very easy to spot and pops out. But so there were publications of what happened to G2 after closest approach. And the interesting thing is that G2 survived. So it didn't get destroyed. We didn't see the fireworks we were expecting. And so that's what was driving the explanation to actually having a stellar object inside that will keep it together instead of just having a gas cloud that will be completely destroyed by passing so close to the black hole. So the reason why you didn't hear so much is that it was not as spectacular as we expected, probably.
All right, we'll take one last question, and then we'll wrap it up.
Hi, I'm Mariana Lazarova. Again, I'm not a reporter. I have a question for Scott. So since you made a conclusion that single quasars are a result of a less violent merger, can you define violent? Like, what exactly do you mean? Does it relate to, is it a major merger, like ratio of galaxy masses? Is it velocities of a proton? Like, what's violent from a scientific standpoint?
Sure, that's a great question. So I think generally when we think of violent, maybe morphological disturbance in the galaxy. So things you could think of visually would be like tidal tails, extreme asymmetries in the visual profile of the galaxy, things like that.
Okay, well, it's 4 o'clock, so I think we should wrap it up. I'd like to thank our presenters again for some very interesting new results. And I'd like to thank all of our audience members. We've managed to fill the room pretty well for each of our briefings. Now, it is true that in the block program and in some of the other schedule materials, there's another briefing listed for tomorrow morning, but in fact, there is no press conference tomorrow morning. That being the case, we have scheduled our next AAS press conference. It will be on Monday morning, January 7th in Seattle, and I hope that I'll be seeing all of you there. Now, if you're a reporter or other press registrant and you signed up for the press dinner tonight, I just want to remind you, we're meeting at La Loma Mexican restaurant at 7:30. There are some maps in the press office. It's just a couple-minute walk down Tremont, so you shouldn't get lost. I look forward to seeing you there this evening. And again, I look forward to seeing everybody in January. And thanks again for a great press conference. Bye-bye.